Welcome to my Module 3 video lecture on solutions about singular points. We've talked about solutions about ordinary points, and we've done a whole bunch of problems, and we've also looked at how to determine if you have a ordinary point or a singular point, and if you have a singular point, is it a workable singular point or not, scientifically or mathematically called regular singular, meaning it's a singular point you could work with, and you have an irregular singular that you cannot work with. So in this section, I'll show you solutions to differential equations that have singular points but workable singular points, known as regular singular. And we'll see the new recurrence relation and a new variable that comes along that you need to calculate and go through the whole setup anyways, regardless of what you're working with. So we start with the method of Frobenius, which is actually the guy that I figured out if you have a singular point, it's possible that it could be a nice singular point, and you can work with it and actually find the solution. 1849 to 1917, and he said if you had a differential equation with variable coefficients, if x equals x naught, and our favorite x naught, of course, is our favorite x naught is, of course, 0, is a regular singular point of a differential equation above, then there's at least one solution that looks like that. So basically, if x naught was 0, you could have written that in much simpler form. You basically would have said that he says that we have a solution that must look like x to the power of n plus r, as n goes from 0 to infinity. And that solution looks very much like if I factor out an x to the r, because that has nothing to do with the index of the summation, it's considered a constant. So if I factor out an x to the r, then I'll have an x to the n as n goes from 0 to infinity. So it looks like, you notice that it's exactly like the solution you had from before, and all that's added is just an x to the power of r on the outside that adds to the solution. And it's that r that we need to find that gets added to what you've done before already. Now, the scenario breaks into three cases. When you actually find your r's, let's say we're looking at a second order, if you actually find your r's, it could be three scenarios where the difference is not a positive integer, the difference is a positive integer, or they're equal. Now, the other two cases are redundant from the first case. You just add an ln here and there. So that's just instructional and cookbook. So if you basically know how to do the first case, the other two are just subsequents of that. So what we'll do is we'll work on examples where once R1 and R2 are determined, you'll realize that their difference is not a positive integer. So you'll know that your solutions y1 is going to be the regular good old-fashioned solution used to find for ordinary points, and you just have an x to the power of r1 outside, and you have an x to the power of r2 outside for the other power series solution. And we'll show you how r1 and r2 are going to be found. So because people get lost in the process of actually doing it, and they lose sight of what the actual solutions at the end are going to look like, because you're going to only find, let me just erase this so I could show you what I want to show you again. You're only going to find, when you're doing this, you're only going to find this part, and a lot of folks forget that x to the power of r1 at the end. So say r1 was, I don't know, 1/2. Then at the very end, people find out the solution, and they find the an, let's say n factorial over n plus 1 x to the n or something, and goes from 0 to infinity. And they think that's the solution, and they forget that the solution isn't just that. The solution is x to the power of 1/2 times that. So that's always forgotten in the Frobenius case. So let's actually go through a problem so you could see how these r's are going to be found. And then once r's are found, then after that, the process is the same thing you've done for ordinary points. So let's look at our first case here. All right. Here we're going to try to solve the following differential equation using an ordinary singular point, a regular singular point, a workable singular point, and see how we could find r's and how to go on and find the actual solution. So my differential equation is 5xy double prime plus 4y prime plus 3y equal to 0. And I am using x naught equal to 0 as my regular singular point. So we'll start with assuming that my solution is going to be of the form an x to the n plus r, and there's the infamous r, n is equal to 0 to infinity. So you notice the only difference is from what we used to start with is that r variable then that we're going to have to find through taking proper derivatives and plugging it back into the differential equation and setting it equal to 0, and from there we're going to be able to find r. And then we'll have to find a solution for each given r value. That's why this is double the previous problem. So you're doing like 2 ordinary points problem for one of these. Anyhow, so let's see how that so-called initial equation is going to be found. Now, let's take the appropriate derivatives of this. So my y prime will be an n plus r x to the n plus r minus 1, and then goes from, yep, not 1. Now this time you can't just up the index because now it does make a difference. That 0 term still has an existing entity that it doesn't go away, so you have to start from 0. Can't move it up to 1. And y double prime here will just be an n plus r times n plus r minus 1 times x to the n plus r minus 2 as n goes from 0 to infinity. So you could see how more tedious the arithmetic here is going to be. It's just a lot of writing. So now I take all of these values and I plug it into my differential equation. So I have 5xy double prime, so 5, now x multiplies the y double prime, multiplies that. So I have 5 summation of n goes from 0 to infinity of n plus r minus 1, x to the power of n plus r. Now minus 2, but then you multiply it by x, so you get minus 1. So that's 5xy double prime plus 4, and then you multiply that by y prime, so n plus r x to the power of n plus r minus 1, as n goes from 0 to infinity, plus 3 times y, which is n equal to 0 to infinity, an x to the power of n plus r, and that whole thing has to equal 0. Now, if I factor out, you notice here, x to the r could come out of the entire thing. So why don't we do that? Because ultimately what the r's I need, that will ultimately lead me into what's called the initial equation that will allow me to find r's, is independent of this x to the power of r that happens to be common in all of 3 of these, and it happens to be a constant with respect to the summation. So it just makes the calculations a whole lot easier if I just pull that out. So pulling out an x to the r out of the whole thing. Okay, so I'll start with, and so I get that out there. That's x to the r, pull it out of the whole thing. So it's a summation of 5an n plus r minus 1 x to the power of n minus 1. You see r is gone, so it's much cleaner. Really doesn't affect the calculations at all. Summation of 4an n from 0 to infinity of n plus r x to the power of n minus 1. And then this becomes plus the summation of 3an as n goes from 0 to infinity, x to the n, and then we close the brackets, equal to 0. So now here x to the r is equal to 0, which is, it can't be, so that doesn't really change anything. So now I could more comfortably work with these. Now remember, our objective from the past hasn't changed. We need to make sure that these 3 power series have the same index and the same starting power of x, so that we could combine the two, so we could actually find a constant and r. Now let's do what we did before. If I plug in the first index into the power of x, for the first one I get x to the power of minus 1. Here it's possible to get negative exponents here. If I do the second one, I get x to the power of minus 1, and if I do this one, I get x to the power of 0. So I have to take out one term out of the first power series and one term out of the other one so that they could both come to 0, so that all start at the same power, so that then we could focus on combining the powers of x is the same as well. So I'm going to just ignore this x to the r initially, because again doesn't enter the computations. But remember, at the end, when we find the r's and the solutions, don't forget to put the x to the power of r behind the actual solution you find, and I'll remind you when I get there. So for now, we're just going to forget about the fact that it exists, because it doesn't really affect anything in our calculations. Now, I'm going to take the first term out of this one, out of the first term, first power series. So I'll have 5a naught, see, and I'm going to use n is equal to 0 in here. So 5a naught, n is equal to 0, don't forget. So n plus r will just be r, times n is 0. So n plus r minus 1 will just be r minus 1, x to the power of n0 minus 1. Plus, then I'll write the next term, which starts at 1. And then I just rewrite the same thing, n plus r minus 1, x to the power of n minus 1. Plus, then I take out the first term out of the second one, so I get 4a naught, n is 0, so r, x to the power of minus 1, plus, now my index goes to 1, and I copy what I have, n plus r, x to the power of n minus 1. Plus, then the third one does not need to be touched, so I could actually write that plus a little closer. So I could just write plus the power series of 3an x to the n as n goes from 0 to infinity, and all that is equal to 0. Now, you guessed it, the equation for r that's going to give us r is going to come from there, what I underlined in yellow. And that's what's going to be called the initial equation, because now what you're going to do is just like what you did before. You're going to put those terms together, and they're going to produce some information for us in terms of finding all the constants we need to ultimately find the solution. And the second one will come from combining these power series and then writing the recurrence equation and then ultimately finding all the constants. So for now, we notice that both of these yellow underlined terms have common x to the minus 1, so I could combine their coefficients. So I have 5a naught r minus 1. Actually, a naught is a constant too, but let's just keep that. Well, actually, let's just pull that out too, so that you could see the whole thing done at once. I could put two things at one. So here I notice a naught's constant, common, x to the minus 1 is common. So if I pull that out, I'll be left with 5r, r minus 1, plus 4, and I'm pulling out the a naught and x to the minus 1, so I'm left with r, and that's just a naught x to the minus 1, and that has to equal to 0. Now, x to the minus 1 can't equal 0, and so here either a naught is 0, or this equation here is 0. And this equation is the equation that's actually going to be used for you to find your r values. And that's what's called the initial equation. Now, if I clean that up, I get 5r squared minus 5r plus 4r equal to 0. I haven't forgotten about my power series. I'm just trying to get this out of the way. So I have 5r squared minus r equal to 0. So if I factor out the r, so my r's are 0 and 1/5. So r equals 0 and 1/5. So those are my two r values, initial roots. Now, and their difference is not a positive integer, so which means I could write my solutions the way I showed it to you earlier. So now for each value of r, I'm going to have to find a recursive relation for these power series, so I can ultimately find the constants, because ultimately, remember, that's what we're looking for. We're looking to find those constants. All right, so I'm gonna start with the smaller one, r is equal to 0. Now remember, if you had more of these, because sometimes you'll end up with two of these equations so for example, you'll have some other ones for value of x. You'll have some function of r here. Let me also remind you of that. So sometimes you'll have two of those, and you'd kind of wonder which r. So for example, this will be like r times 2r minus 3 times r plus 5 or something. And you'll kind of wonder from which equation do I find r, because if I want to find r for all of them, I'll have like 6 different r values. And what you could remember, you always go with the smallest power of x, you take that coefficient. So even if you had an x to the power of 0 here, you wouldn't have to worry about that. You only go with the lowest power of x and you only focus on the coefficient of that. And that's where the r is going to come from. That's your original initial equation. And these are called the initial roots. Okay, great. So let me get rid of that. All right, so r is 0, r is equal to 1/5. So now let me take the power series and clean them up. So just don't forget r is equal to 0 and 1/5. So I'm going to delete all of these because I'm done with the constants. All right, so I'll just write this here, r is equal to, let me actually write it. Here I'll say r is equal to 0, comma 1/5. And actually I'm going to highlight that yellow. There you go. And let me delete that. All right, so now let's look at my power series. So let me write them again. I have, actually let me try something smarter. So I can just grab this. Let's see if that was a smarter move. Copy it and paste it. Yeah, that's a smarter move, so I don't have to rewrite it. Ha ha ha. So let me grab the second one. I can cheat that way. Copy here, paste. So there. And then I can take the third one. Oh, this is fun. So I can take the third one now. And I can say copy and then paste it here. And that's the third one. So that's a plus. Fantastic. So I brought them all together. So now I need to make sure the powers are the same. So the first two, yeah, it looks like, yeah, even though I have 2n minus 1, so you would think I'll change the other one to n minus 1. I kind of want to just change everything to n and then lower the indices to 0, and that will work out. So from the first one, I'm going to lower the index by 1 unit, so I'll go back to 0, go down to 0. That means I have to increase the n by 1 unit on the inside, so 5, an plus 1, n plus 1 plus r, n plus r, plus 1 minus 1 goes away, x to the power of n, plus, same here, I lower the index by 1 unit, so I increase the inside n by 1 unit, so it'll be n plus 1 plus r, x to the power of n, plus I don't touch the third one because it's already x to the n from 0 to infinity, and all that is equal to 0. So you notice that now I have my equation here, that I have my 3 summation all the same, so I could combine them together. So I have 5an plus 1, n plus 1 plus r, n plus r, plus, and of course there's a summation here, n is equal to 0 to infinity, and I have a bracket here, plus 4an plus 1, n plus 1 plus r, sorry, there's no x, and then plus 3an, and that's close the brackets, x to the n equal to 0. So there is the coefficients all pulled together. Now this must equal 0. So I have the 2n plus 1 terms I can pull together. So I have an plus 1. So I pull out the n plus 1 plus r. So I have 5 n plus r, and here I'll have 4 an plus 1 that comes out, and you'll just have 4, that's right, plus 3an, and that's equal to 0. So this gives me 5n plus 5r plus 4. So then I have an plus 1 times n plus r plus 1 times 5n plus 5r plus 4 equals minus 3an. Now here I have an plus 1 equals minus 3an, divide by, actually I can keep the an out, minus 3an here, and in the denominator I'll have n plus r plus 1, 5n plus 5r plus 4. So this is my recursive relation. So now I need to find this, to use this to find all my constants. And now let's remember that now we have two scenarios, r is equal to 0 and r is equal to 1/5. So we have to solve and find the sequences for each r, and this is when it's just the double of the work we used to do for ordinary points. Because ordinary points, you just go through this once, but here you have to go through it for r is equal to 0, then you have to go through it for r is equal to 1/5. So that's what makes the extra work, and that's it. It's just more tedious work. So let's start with r is equal to 0. If r is equal to 0, then my an plus 1 will be minus 3, will be n plus 1, and this will be 5n plus 4 an. So this will be my recursive relation here. So which is much more pleasant than the one above it. Okay, and here you will find n is equal to, you'll let n is equal to 0, 1, 2, 3, and so on, to find different values for your constant. So I'll do that with you, and then I just want to show you if r is equal to 1/5, then you just replace r with 1/5 here. And I just want to find that out for you as well. So an plus 1 is equal to, so it's minus 3. So n is, r is now 1/5. So I'll have n plus 1/5 plus 1, and 5n plus 5 times 1/5 plus 4 an. So an plus 1 becomes negative 3. So this part becomes 5n. 5 times 1/5 is 1 plus 4 is 5, so plus 5. And here I have n plus 1/5 plus 5/5, 6/5. But the good news is a 5 comes out of that power. So if a 5 comes out of there and that turns into n plus 1, that will turn this one into 5n plus 6, and the fraction will go away. So it actually is simpler. So if I just delete all that and draw my line, my denominator is simply n plus 1 times 5n plus 6, and I can just delete the rest. So those are my, I can draw my an a bit closer. So there's my an, and there's my second recursive relation. Okay, and this is for r is equal to 1/5. So each one of these will give you a different solution. Now for the first one, an plus 1 is equal to negative 3 over n plus 1 times 5n plus 4 an. For that one, I'll do that one for you. If n is equal to 0, then I'll get a1 is equal to negative 3 if n is equal to 0. So you get 1 times 4, which is 4. So you get negative 3/4 a naught. If n is equal to 1, you get a2 is equal to negative 3 over 18 a1, which becomes, but a1 is negative 3/4 a naught, so negative 3/18 times negative 3/4 A naught, and that becomes 1/8 A naught. Okay, so if n is equal to 2, now A3 becomes -3 over 3 times 14 A2, but A2 is 1/8 A naught, so if you combine those, it'll become -1 over 112 A naught. Now if I write my solutions with these, I'll have y1 of x. At this point I have enough coefficients to write my solution. Remember, my solution always has to start with x to the power of r, which was what? Even though it's 1, you still have to respect it and start with it. So it starts with that. And now I can write my solution, which is A naught, because it looks like everything is written in terms of A naught, so it's A naught. And then the next term is minus 3/4 A naught x. And then the next term is plus 1/8 A naught x squared. And then minus 1 over 112 A naught x cubed, and so on. So then I can actually write my first solution as A naught 1 minus 3/4 x plus 1/8 x squared minus 1/12 x cubed plus so on, and there is my solution. So at least a part of it, first one. Let me see if I can do this. Nope, that didn't work. I'm gonna pull this off. There you go. So there's my solution, and my first solution. Now I'm going to be able to find the same thing by taking this second recursive relation and replace n with 0, 1, 2, 3, 4, and so on, and to be able to find the same situation as you did here. And that's already written in the lecture notes, so you could follow through. I don't need to do the same thing. It's the same calculations. And you get your second solution. I will write your second solution. You're going to get from that for r is equal to 1/5. So y2 of x would be, again, a naught will be a constant, will come out, x to the power of 1/5 this time, right? Because the second r is 1/5, so we have that on the outside. And your power series will be 1 minus 1/2 x plus 3 over 44 x squared minus 3 over 704 x to the third plus so on. So that becomes your solution. Now, of course, it's a different A naught because it's a different R. So you could just call it A1, or I mean, it's just a different A naught. I don't know how else to write. It's A naught hat. It's just a different A naught, not the same. So when you're actually writing, so here's your second solution. So when you're actually writing the general solution, you could just say y sub g, general solution is just C1 y1, which is 1 minus 3/4 x plus 1/8 x squared minus 1 1/12 x cubed, and so on, plus C2 times the second solution, which is 1 minus 1/2 x plus 3/44 x squared, and so on. So there's that notorious C1y1 plus C2y2 scenario for the actual general solution, which you knew from module 2. Thank you. There is my general solution, and there is my lecture on this particular example, solving the solution of an ODE using a workable singular point or a regular singular point.